Given are the four options. Which of the following is false? First is the set of all bijective functions on a finite set forms a group under function composition. First of all, bijective function means function is 1 1 and onto. 1 1 and onto imply that range of the function is equal to codomain of the function. That is, every element, suppose this is a function from a to b, from set a to b there is a function, then every element of set b must be image of some element of set a. This is the meaning of bijective function. Given that there is a set of all bijective functions on a finite set forms a group under function composition, we have two things given. First thing is set of all bijective functions. This is a set, all the bijective functions on a finite set. Second is there is some operation. This operation is function composition. Now whether this structure is group or not, question mark, we have to check it. In order to become a group, four properties need to be satisfied to become a group. Properties are associative, closure property, presence of identity element, and every element in the set must have its inverse. If four properties are satisfied, then this structure is group. Now we will check one by one. Suppose that there are several functions, it contains all the functions. I am taking one function, we are taking two functions f1 and f2. From this set we will apply composition operator on these two functions. If we get a function which belongs to this set, then a closure property will be satisfied. For example, there is a function 1 2 3 4 1 2 3 4 like this. 1 mapped to 2, 2 mapped to 3, 3 mapped to 4, 4 is mapped to 1. This is our first function. Second function is 1 2 3 4, again 1 2 3 4, like this way, 1 2 3 4. This is our second function. When we apply function composition, that is f1 dot f2, will get a third function f3, which is 1 2 3 4 1 2 3 4, 1 to 2, 2 to 1, 2 to 3, 3 to 4, 3 to 4, 4 to 3. I am correct, 3 to 4, 4 to 3, yes. 4 to 1, 1 to 2. So 4 is mapped to 2. This is also a bijective function. The result is a bijective function, and we know that this is a set of all bijective functions. So f3 belongs to this set, hence closure property is satisfied. Closure is satisfied. Now we will check another property, that is associative. First we check whether identity element is present or not. See, second property is presence of identity element. A function f, when composited with identity function, the result is function f itself. So let if is equal to 1 2 3 4 1 2 3 4 1 2 3 4. This is the identity function. let's see whether it works or not. We have function 1 2 3 4, 1 2 3 4, 1 2 1 2. When we composited both if with f2, the result we get 1 to 1, 1 is 2, 1 to 1 and 1 to 2, 2 to 2, 2 to 1, 3 to 3, 3 to 4, 4 to 4 and 4 to 3. So what result we are getting? We are getting the function f2 itself. See, when if that is identity function is composited with function f2, we are getting function f2 itself. So our identity function is working, hence we have presence of identity element. Now we will check whether associative is satisfied or not. For associative, if f1 composited with f2 composited with f3 is equal to f1 composited with f2 composited with f3, if LHS is equal to RHS, then associative will be satisfied. See, f1, suppose f1 is our identity function, then f1 composited f2. If f1 is, let f1 is equal to if, then if composited f2 composited f3, if composited f2. This is question mark, it is not equivalent. It is decidable, we have to decide this. Again, if composited with any function is function itself. If composited with f2 is f2 itself, f2 left with f3, hence both are equal. So associative property is satisfied. Now I will check whether inverse is present or not. See, we have a set of all bijective functions. We know that a bijective function is invertible in nature. So every bijective function will have its inverse. Hence we have proved that this set of all bijective functions is closure in nature, presence of identity element. Third property, that is associative property, is satisfied. Fourth property, that is inverse, is also present. So this forms a group because all four properties are satisfied, hence it is a group. So the option A, forms a group under function composition, is correct. Now we have to find which is false. Now second option says that whether 1 to p minus 1, where p is a prime with multiplication modulo p, is a group or not. Again we will check for properties, that is closure property, associative property, presence of identity element, and every element has its inverse or not. Let's take example. P is equal to 5, then the structure will become like this: 1 2 3 4, because this is p minus 1 and multiplication modulo 5. Now take any two element. 3 multiplication modulo 5, 4 is equal to 12 modulus 5, that is equal to 2, and 2 belongs to this set. So closure we have taken two elements 3 and 4, applied this operator, the result is 2 and 2 belongs to this set, so closure is satisfied. Now we will take associative, whether it is associative is satisfied or not. 3 multiplication modulo 5 4, again applying operator 2, whether it is equal to 3, if both are equal or not. 4 2 is 8, 8 modulus 5 is 3, 3 3 9, it is called result is 4. 3 4 is 12, it is 2, 2 2 is 4, that is result is 4. 2 2 is 4, 4 modulus 5 is 4. So both LHS RHS are equal, so associative property is satisfied, closure is satisfied. Now we will see whether identity element is present or no. Not. Here E is equal to 1 is identity element which is present, so identity property is also satisfied. Now we will check inverse. See, identity element is inverse of itself, so inverse of 1 is 1, 2 modulo 5 and 3 is equal to 1, so 2 inverse is equal to 3 and 3 inverse is equal to 2. 4 modulo multiplication modulo 5 into 4 is equal to 1, so 4 is inverse of itself, hence inverse property is also satisfied. All four properties, first property associative, closure, identity, inverse is satisfied, so this is a group. Yes, option B is also true. Now we will check option C. Option C is set of all strings over finite alphabet. Let's example, sigma is equal to a comma b, and given is set of all strings and operator is concatenation. So if you will check similarly as we have checked in other previous options, closure is satisfied, associative property is also satisfied. Here identity element is epsilon. Set of all string means a comma b, clean closure. This is set of all strings over a comma b, so epsilon identity element belongs to this set, so identity is satisfied, associative is also satisfied, closure is also, because s1 s2 s3 is equal to s1 s2 s3. Here both are equal. Take two string s1 s2, the result s1 s2 will belong to this set, so closure is also satisfied. But we can't have inverse of all the strings s1 when concatenated with any other string. We can't get epsilon. Inverse means, suppose we have taken a string s, when concatenated with its inverse we should get epsilon as the answer. But for any string s, there is no inverse present, there is no other string which can be concatenated with s, so that the result will be epsilon, so inverse operation fails. Hence option C is not a group, it does not forms a group, so it is false. Option D is a famous theorem on subgroup, you may have read in set theory, so it is correct.